Okay. So I'm gonna move in and get a little bit of chapter 4 done. I'm kind of combining two sections here. There's a little bit of stuff that it's okay for us to leave out in 4.1 and 4.2, so we'll leave out the stuff that we don't absolutely have to get to, and then we'll just kind of combine the parts out of the two sections that we really got to have together. Okay. So still dealing with functions. In chapter 4, we get two new types of functions that we deal with. The first one we're going to look at today is called exponential functions. And then we'll look at logarithmic functions, logarithms, next time. We'll do a little bit with them, and that'll be as far as we go in this class. As far as we go. Yep. So let's look at the calendar. So I think it'll be on the 22nd. That'll be 2 weeks from Friday. And then that'll give us the 26th for anybody that needs or wants to take the final exam. We'll review for it on the 26th in class. Okay. Yeah. So, oops, sorry. Not 22nd, 21st for us because we're Tuesday, Thursday. So I got one today, and then 3 more lectures and a review day. And so we won't have too much more. Okay, especially for Tuesday, Thursday classes, we're getting pretty close to the end here. Okay. All right. So this section won't be a really long lecture. So that'll be good. We'll kind of try to reward the ones that are here today. Okay, we're kind of thin. We'll try and get through it. Okay. So an exponential function. Let me get that. So we need to see what they look like. Goodness. Okay, so we've got some. That's a B. That's an ugly looking B. Let me see if I can do better. So we got some number raised to a variable power. Okay. So B and it's not just any number. We want it to be greater than 0, less than 1, or bigger than 1. Okay, so that might be a little confusing. So either our number needs to be between 0 and 1, that's our B there, or it needs to be bigger than 1. If B is 1, it's not going to be an exponential function anymore because 1 to any power is just 1. So our function would simplify down to f of x equals 1, and that would be a linear function. So we need it to be between 0 and 1 or bigger than 1. And that number B call that the base. Okay. So here, b is what we would call the base. And then we've got a variable exponent. Okay. That's an exponential function. Okay. So if you look at our conditions for the base, it says it's got to either be between 0 and 1, or it's got to be bigger than 1. Sometimes it's going to look like that's not true, because it's okay to put a minus sign out in front of the whole thing. It's just that the number b itself can't be negative. So what we're saying there is like negative 1 to the x would not be allowed, because in that case our base would be smaller than 0. But what you will see, 1's not a good choice, let me do 2. Okay. What you will see sometimes is this, and that's okay, because what that's really saying is we've got minus 2 to the x. It's just a minus sign out in front of the whole thing. The base is not negative. So if you see it written like this, that's okay. The base is not negative. The base is still 2. It just happens we have a minus sign out in front of the whole function. Okay. But here, where we have a minus 2, that's not allowed. If you tried to do one like this, where you had a negative number actually raised to a power, you don't get a function. It fails some of our test. So you at least don't get an exponential function. Sometimes it would be a function, sometimes not. Not an exponential. Okay? All right, got an idea of what an exponential function is? Got some number raised to a variable power. Okay. So let's experiment with one a little bit then. Okay. And there's an exponential function. And the way we could describe that one is we could say our base is 3. Okay. So our big number is 3. Okay. So if we wanted to find like f of 1, we wanted to evaluate our function at an x value of 1, we still do the same thing we've been doing. We just plug in where the x is. That would just give us 3 to the first power, and anything to the first power is itself. We could do f of 2. Then that would give us 3 squared, or 3 to the second power. That means 3 times 3, so that's 9. One thing that's pretty remarkable about exponential functions is the y values get big really quickly. So like if we're skipping some here, but like we wanted to do like f of 10, that'd be 3 to the 10th power. I'm going to punch it on the calculator. So just by the time we get to an x value of 10, that's already 59,049. And let's skip ahead just a little bit more. These things grow really quickly, so I wanted to find f of 20. Let's see. That is 34,867,840. Nope. Hang on. I got my commas in the wrong place. Let me just write the digits down and we'll put them in. So 3,486,784,401. So they grow really rapidly. We would have just a hard to imagine number by the time we get to f of 30, right, when we do 3 to the 30th power. So you'll hear that talked about sometimes. You'll hear things talked about and they're saying it's growing exponentially. That's what that means. So if we want to give some comparison here, if we let's switch their places, do x to the third. So that would be x to the first, so that's, it'd be 1 to the third, so that would be 1. 2 to the third would be 8. So those two, they're not that far apart, but when we go to f of 10, that'd be 10 cubed, so this is only 1,000. Okay. When we go to f of 20, I'm not going to mess that up in my head. Let's just do it now. That's only 8,000. So the exponential gets to the big numbers a whole lot quicker than just like if we had like x cubed. If we had a power function, is what you would call that. There's some kind of polynomial. All right, so if something's growing really big, a lot of times people don't use it like technically correct, but sometimes so people will just kind of use it informally and say if something's growing really big, it's growing exponentially. Here you got exponential growth. That's what they're talking about. They're saying it's getting big really quickly. Okay. And if you're using the calculator, you can even, you can still evaluate these at weird numbers, like you can do f of square root of 2. Okay, that's not easy to do by hand, but if we're using a calculator, that's just 3 to the square root of 2 power. So let's see what that's going to come out to. Because I think WebAssign throws some weird numbers at you every once in a while. So that's like about 4.7288. So you just get a number out of it. Okay. All right, so let's talk about what the graphs of these things look like. Okay. So let's go back generic. Just talk about b to the x. Okay, so if b is positive, not positive, if b is bigger than 1, sorry, and then our graph is going to look something like this. Couple of remarkable things here. You look as we go off to the left, our y values are getting really small. But getting closer and closer and closer to the x-axis, but it never actually gets there. So that's what we call an asymptote. So the line y equals 0, or the x-axis, is a what we would call a horizontal asymptote. Okay. I think that's the right spelling. Let's see if I got anywhere up here. I always forget if there's one S or two S's in that. One S. And then the other remarkable special thing about the graphs of all of these exponentials where our base is bigger than 1, well, really this part applies in any case, is that here where our y-intercept, where our graph crosses the y-axis, that point is the point 0, 1. Okay. 0, 1. Okay. Because if you take any number and raise it to the 0th power, any number that's not 0, and raise it to the 0th power, you're going to get 1. Okay, so it doesn't matter what the base is. If you raise it to the 0th power, you get 1. So that means on all these exponential graphs, we've got the point 0, 1 on the graph. Okay. That's our general shape. And the way I've got it drawn would be pretty zoomed in, because if you zoom out, we said these things grow really quickly. So if you zoom out a little bit, this thing's going to look like it's going almost straight up because it's growing so fast. Okay. All right, and then over here, our y values are getting smaller, okay, because when we raise something to a negative exponent, that turns it into a fraction, right? So we've got fractions over here getting smaller and smaller. Okay. So that's the case where our base is bigger than 1. If our base is smaller than 1, so between 0 and 1, it's going to look almost the same with one difference. And the one difference is that it's going to run backward. Okay. It's still going to go through the point 0, 1. Okay. The line y equals 0, or the x-axis, is still going to be a horizontal asymptote. Okay. It just flip. Okay. The reason why it does that is if we have, so we're talking about b being a fraction, and so let's look at an example. Okay. So that would be 1/2 to the x. Okay. If we remember exponent rules, we could move that 2 up to the top by making it a -1, and then I think it turns into this. Okay. So the effect, if we have a fraction as our base, it's really like we've got the flipped version of the fraction raised to a negative exponent. We'll talk about how that flips it in just a second. But you can just remember, it's okay, just remember that if our base is bigger than 1, it gets big on the right side of the graph. If our base is a fraction, if it's between 0 and 1, it gets big on the left side. It gets big on the left side. Okay. Questions so far? Hanging in there? Doing the best you can on a rainy day? All right. So that's our basic graph picture. So let's kind of go back in time a little bit. And talk about what the different transformations of the graph look like. So remember, we got horizontal shifts, vertical shifts, x-axis, y-axis reflections, and that's all we're going to be worried about. We're not going to worry about stretching and shrinking with these. Stretching and shrinking works exactly the same way. It just looks weird with exponentials. Okay. So let's start with a generic exponential function. Okay. So if we add, well, let's do it this way. If we add some number out to the side like that, okay, looks pretty much the way it did with our other functions. Okay. So that's going to be shifted up. So it's plus. If it was minus, shifted down. Okay. So still, if we have a vertical shift, you just have plus or minus a number out on tacked on the end of the thing. Okay. Remember, for horizontal shifts, we add or subtract some number with the x. Okay, not just out on the end of the function, we add or subtract some number with the x. So the way that looks with exponentials is our number we're adding or subtracting will be in the exponent. Okay, so we got a little x plus c up there. So since we're calling it plus c, it'd be a shift to the left. If it was minus c, that'd be a shift to the right. Those are what our vertical and horizontal shifts look like. And let's talk about our two reflections. There we got negative b to the x. That's okay. That minus sign is not with the b. It's out in front of the whole thing. Okay. If the minus sign was with the b, we would have to have parentheses around it. And so it's like saying like the opposite of b to the x. That's what that's saying. Okay. So since we've got a minus sign out in front of the whole function, that's an x-axis reflection. It's going to make the part that was up at the top go to the bottom. And that means it. Which is the top of the bottom. Okay. And then a y-axis reflection where we switch left and right. That's really the same thing that's happening if we have a fraction for our b, for our base. So that's what happens if we put a negative up in the exponent. Okay. So those are the four we're going to be concerned about. Shifts up and down, shifts left and right, switching top and bottom, switching left and right, reflecting. Okay. So we got that function, negative 8 to the x plus 1. What kind of transformations have been done? I usually start with the vertical translations first because they're easy to pick up on. We just got a plus 1 out there. So that means our graph has gone up 1. Okay. And then the other thing we got to pay attention to is this minus sign that's out in front of everything. Okay. So if we have a minus sign out front of everything, that switches top and bottom. So that's an x-axis reflection. Okay. So if we wanted to make a rough sketch of this graph, okay, the parts in the top is going to go to the bottom. It gets reflected over the x-axis, and then it's shifted up 1. Okay. So one thing we can do, we can keep track. So we know if we start with an exponential function, we got the point 0, 1 on our graph. So if we reflect that over the x-axis, that's going to give us the point 0, negative 1. But then we got to go up 1 unit. So we'll be at the point 0, 0. And then our graph's going to look like this. Okay. And anytime we do one of these vertical translations, that moves our horizontal asymptote. So normally on an exponential, the horizontal asymptote's at y equals 0. But since we went up 1, our horizontal asymptote would be at y equals 1. If we had had a minus 2 out here, then our horizontal asymptote would be at y equals negative 2. So it would be 2 units down. So it just, when we do a vertical shift, it moves the horizontal asymptote as well. Okay. So this graph would have started off looking like this. Right? Small on the left, big on the right. Then we reflect it over the x-axis, so it turns it upside down. And then we've shifted up by 1 unit, so we got to move up a little bit. Right, so part of the assignment is multiple choice graph matching. So you look at what kind of transformations have been done, and then you can pick it out for multiple choice. Okay. You don't have to actually draw the graph on any of them. Okay. All right, so all that applies to exponential functions in general. Okay. There's a special exponential base that comes up a lot, comes up in a whole bunch of different fields of study. So it gets its own special treatment here. So let's talk about it. So this is a special number. It's like pi, in that if you try to write it down as a decimal, the decimal keeps going forever and ever, and it doesn't repeat. So you can't actually write the whole thing down. Like with pi, it goes forever and ever. And we call that irrational. So in those cases, we usually give some kind of symbol to the number, like we do with pi. This is probably the second most famous irrational number, maybe. It's the number that we call e. Okay? And that number e called the natural exponential. Or sometimes you'll hear it called this, named after a mathematician. And it's German, so we don't ever say it right. The way you pronounce it, as close as we get in Alabama anyway. You say it like Oilers. It looks like a really Alabama name. It looks like Euler. Okay? Whether you pronounce it Euler. And we try to write it as a decimal number representation. So pi we round to 3.14 a lot. If we round e to 2 decimal places, we would call it 2.72. I think, yeah, WebAssign asks you for a few more decimal places here, so let me give you enough to make WebAssign happy. And it's 2.71828 if you go out 5 decimal places. So between 2 and 3, but closer to 3. And it's really amazing how often this seemingly random number pops up. Okay? You'll be taking an accounting class, and then there's E. You'll be taking an engineering class, and then there's E. Okay? You'll be doing something in some social science class, some psychology class, or something with some kind of formula in there for a model, and then there's E. It pops up all over the place. Okay? So what we're going to be concerned with mostly, at least in this section, is using e as the base for an exponential function. So e to the x power. All the stuff we learned about the graphs, that still applies here. So e to the x, if you don't put numbers on there, it looks just like our other exponential functions. You still have a horizontal asymptote at y equals 0. So it goes through the point 0, 1. So all exponentials with a base bigger than 1 have that same basic shape. The only way you can really tell the difference is if you put them on the same graph and compare them. So like 3 to the x would be, it would get big a little bit sooner. 2 to the x would get big a little bit later. So this one falls in between those. Okay. Falls in between those. Okay. And for right now, I think the only other thing we need to talk about really is just evaluating a function using this. So because e is a messy decimal number, it's not like a whole number or anything. Really, the only good way for us to evaluate these things with a calculator, the only time efficient way. So there are a few values like 0. So if we do e to the 0, anything to the 0th power is 1. Okay. And then another easy value for exponential functions, if we've got e to the 1, that's e, so about 2.72. Beyond that, we just have to use a calculator. And your calculator should have an e button on there. If you find out you have trouble finding that on your calculator, bring your calculator to class next time. I'll be glad to help you find that. So let's see what this one comes out to give you a reference value. So if we want e to the 5th power, so I'm going to round to 3 decimal places, so that's about 148.413. Something like that. And then doing translations on the graph works just like the other exponentials. And if we've got like e to the x plus 2, that means our graph's gone up 2. And if we have e to the x minus 4, well, we got that in the exponent. This minus 4, since it's in there with the x, it's going to be horizontal. So minus means to the right on these, so that would mean we've gone to the right 4 units. If we have minus e to the x, the minus sign means we've got an x-axis reflection. Minus sign out front. And then only one other type, now that's if we have e to the negative x. In that case, the minus sign in there with the exponent, just like with the other exponential functions. And that's a y-axis reflection. Questions on any of that? Not from the ones of you that are here. Is it going to be the people that are not here that are real flipping confused? Okay. Oh, that's it. There's not too many. Let's see how many did I put in this assignment. 10. Not bad. Oh, okay. Well, yeah, one other thing to mention. I'm glad I looked at this. The only other thing to mention, WebAssign on a few of the problems with the graphs will ask you for the domain and range. Okay. So for exponentials, so for exponential functions, Assuming they haven't been reflected or anything like that. The domain, we can use any x value, so the domain's negative infinity to infinity. And if our graph hasn't been flipped, and so like if just for like b to the x, right, then our range remember we got a horizontal asymptote at y equals 0. So we can't actually get to 0, but anything bigger than 0 we can get to, and then these things go up. But you have to adjust the range when the graph has been transformed. And so if we've done any kind of transformation, if we've done a vertical shift, you just add whatever the vertical shift is here. So the range will start here. If you do y-axis reflection, nothing changes on the range. But if you do an x-axis reflection, then instead of going toward infinity, it's going to go toward negative infinity. So you'd have to switch the sign there. Okay? Just look at how that changes if it's flipped. But the domain's easy, and the domain is going to be negative infinity to infinity. Questions? All right, it's supposed to be drier this afternoon, I think, so if you had outside plans, maybe you still get to do them. If you're here, make sure you're on the sign-in sheet before you leave. Might as well get credit for being here today when a bunch of people weren't.